Hello, and hopefully you can hear me okay. Welcome, it's Thursday evening, it's the 11th of May, and we're going to be looking this evening at thermodynamics and Gibbs free energy. We looked at a bit of thermodynamics just last week, on Monday night, where we looked at Born-Haber cycles. If you want to catch up with that webinar, please just go to the website and check out our past webinar page. If you're in the chat room here, please do just say hello so that I know that we're online, and we'll get started in just a minute or so. Like I say, we're going to look at Gibbs free energy this evening. We've had a few requests coming through on the site. Quite a few people have asked to do some work on KP, partial pressures calculations, and also period 3 oxide. So next week, really sort of to finish off the paper 1 webinars, we'll look at some of the KP calculations as well as some of the period 3 oxide experiments, and then we'll look at some after that. We'll probably be a couple of weeks out and we'll start doing some of the past papers. If you're just checking out the site for the first time or contemplating joining, we've got heaps of resources available. I'll just bring that up on the page now. Like I say, we'll start in a few minutes time. If you've not already done so, come and have a look at our site. Oop, here it is. Where's it gone? Is it going to come back for me? Here we go. We've got heaps of stuff on the site. Do check out our past webinars. Here you'll find all the information, all of the resources that we've got available, the past papers and the practical work, so on and so forth. So do come and check that out. We've also got heaps of past paper questions, past papers, and plenty to keep you going. Okay, I'm just gonna get rid of this, and let me just find my chat again because I heard it pop. Hello, Anon 3359. Good to have you on board. I'm going to start the chat. We're now sort of 8:32. We want to get going pretty sharpish tonight. As ever, if you hear either my sound disappear or the video stops, please do let me know in the webinar chat, and I can double check and make sure that we're working. Okay. Evening, 9502. Like I say, I hope you don't mind me calling you that, but there's not much else I can call you really on the basis of the lack of the names there. Right, so let's have a look. 9502. Well, I'll show you what we did on thermodynamics, because I'll just pull us through to where we got up to. We're in the general section of thermodynamics. We looked on Monday, we went through and we looked indeed at Born-Haber cycles, and we did all of the key points, and we have indeed done thermodynamics here in the sense of Born-Haber cycles. This evening, we're just going to polish off our Born-Haber cycles by looking at entropy and Gibbs free energy, which is sort of in the general topic area of thermodynamics. All right, so we're going to look through at entropy and Gibbs free energy. So you're absolutely right, though. We have looked at the general bit on thermodynamics. Right. So in the AS course, you looked at enthalpy changes. And what we see in the A2 course, the year 13 course, is that reactions are not only dominated by the energy change, but also this thing called the entropy change. So here our entropy, I'm just trying to make this screen a little bit bigger so we can see. There we go. So we're looking at thing of entropy, and essentially, certainly at this level, we measure entropy. It's a measure of the disorder of a system. All right, and a couple of important things here. The first is that more disorder is equal to a more positive entropy value. All right. And obviously less disorder is a less negative entropy value. The other side of things is that we can have a look here at what we mean by disorder and how that can change. As I say, we've got a host of things here that changes. Just if you're saying hello in the Black chat room rather than the live webinar, I won't be able to keep up with any of those chats during the chat room. We're only using the chat in the blue webinar. I see a few things pinging off in there, so apologies if I don't say hello there at all. All right, okay. So more disorder equals more positive entropy value. And the other thing is entropy's also got a sign of S. And we have units here of entropy, which are in joules per Kelvin. So we're talking about degrees Kelvin now rather than degrees Celsius. Joules per Kelvin per mole. Notice that this is slightly different from an enthalpy value. Enthalpy changes H are in kilojoules per mole. So our entropy value here, we've now importantly got this temperature dependency in that we need to be aware of this evening. And what we're going to see is that as we change the order of a reaction, as we increase disorder, we've got two important states here in which we can see that. We're going to have a look at that. And we'll look at the first instance here where we're looking at solids, going through to liquids, going through to gases. Now, there is, as I say, a measure of disorder as we go across from left to right here. We are increasing disorder. And as we increase the disorder, we become more positive entropy. And I'm going to use S for the entropy throughout this. And I can measure the change in entropy of the system as delta S. Here we go, it's theta. And this is equal to the entropy of any products, or the sum of the entropy of the products. This sign here meaning the sum of, take away the entropy here of the reactants. Now what that means is, if I was to draw or plot a graph here of the entropy change as a function of temperature, and I'm just going to do that down here, I would see for my solid going to a liquid to a gas that it would gradually, I've got entropy on the side, I've got temperature here, and as I gently increase, I'll do this in red, I'll then see a large jump here, and this jump is due to a change of state. And then I would then become a liquid, and I would see an increase again. As I turn from a liquid into a gas, again I'd have an increase in entropy. And again another change of state. Just heard my chat ping. Okay, good question. So what's the difference between entropy and entropy change? So entropy change, all right, is the difference between the products and the reactants, whereas an entropy value we can have for individual items within, let's say, the products or the reactants. So we're always interested in how that change in energy occurs. Okay. You're absolutely right, Kay, that entropy is disorder. But often what we're interested in when we're looking at our reactions is the change in entropy, that is the delta S. But individual molecules will have a finite entropy from which we can calculate a value. All right, so that's what we observe for a solid, a liquid to a gas. The other example that we see here is if we go from a solid to a solution, as we go across again, we are seeing an increase in entropy as we go from the solid to a solution. Uh, so, Jay, yeah, we need to be aware here of what the entropy of the system here is. So we need to know the change in entropy is simply the products minus the reactants for AQA. Again, just be aware, all of the topics that I do are specifically related to AQA. All right, so if we're now looking here, I'm just going to take a snapshot of this particular one and we'll have a look. We'll blow this up so we can actually see it here. Here we go. And we can identify what we'd expect here the change in entropy to be for each of these. So here we go from sodium chloride to sodium chloride aqueous. We're going from a solid to an aqueous solution with dissolved. We'd expect here the change in entropy to be positive. We're not going to worry too much about exactly what that would be at the moment, but it'd be positive. Liquid sodium chloride to solid sodium chloride. And we will see that this is negative. And on 2492, I'll take that question in just a moment. I'll just go through these entropy changes and talk about that in a minute. Then our next one here, where we've got 203 gas to 302 gas, where we've not got any change in state. But since we've now got here an increase in the number of molecules, we would see the difference between the products minus the reactants, we would have a positive entropy change. Between N2 plus 3H2 going to 2NH3, we've got more molecules on the left-hand side than we do on the right-hand side. We're all in the gaseous state, so this one, we would have a negative entropy value. In the hydrogen gas, with the iodine gas going to form 2HI, this case, there would be a change in entropy because the different ways that we can orientate the molecules probably in the reactants would be slightly greater. However, this is going to be extremely small and it's probably going to be round about 0. The final example here where we've got copper carbonate going to form copper oxide plus CO2. This is thermal decomposition. We're going from 1 molecule to 2, so we'd expect a positive entropy change. But importantly here, we've got a significant change because we're going from a solid to a gas. So this would most definitely be a positive value. So we've got a few things to consider there. What causes a change in entropy? Well, we've got initially the change of state, but also, as we alluded to here, is we've got the idea that a change of state, but also an increase in the number of molecules will also lead to an increase in entropy or a increased positive value. Now, excuse me just a second. We see this particular effect in the increase of number of molecules going to entropy when we look at the transition metal chemistry, where we see something known as the chylate effect, which we looked at when we've looked at the transition metals. I'm not going to go into the chylation effect in too much detail. Okay, I'm just going to pause there. I'm going to take a question here, which is from 2492, which says, does a reaction favor a particular entropy, e.g. negative or positive? It's a really good question, and what that alludes to is what we're going to look at in a minute, which is the idea of Gibbs free energy. Now, I can't remember if we go on to this side. Yes, well, actually, I'm going to come down here and we'll look at this slide. Gibbs free energy is a measure of the energy in the system and also in a reaction. The key thing that it tells us, if we got the Gibbs free energy being less than or equal to 0, then this defines a reaction as feasible. All right. Now, what we mean by feasible is quite unique in chemistry. It means that the reaction will go without further addition of energy. All right. And this is one of the key concepts within the Gibbs free energy. And the important thing is here with 2402's question being, will it favor a reaction being when the entropy is positive or negative? That this Gibbs free energy is a culmination of two factors. The first being the entropy change, and the second being the entropy change. So we've got the enthalpy change, delta H, here, and we've got the entropy change here, which is delta S, and that's the entropy change of the reaction. Yes. Okay, so yeah, the wording we really need to use here is feasible. Spontaneous is going to depend on something like the activation energy that we're going to have. Feasible is the better term to use in this instance rather than spontaneous. All right. Now, depending on this question about whether a reaction would be favored, whether we're positive or negative, we'll look at possible scenarios in a minute. But the key here, certainly if we're talking about something like the chillate effect, if delta H is low, going back to our question before, if delta H is approximately 0, and this would happen with transition metals where you've got a change of ligand, which you might be going from something like ammonia, and you're going to form a bidentate ligand where perhaps you've got two ammonias being swapped for a diamine group. The enthalpy change for that sort of reaction, that ligand exchange, is going to be about 0 because you're going to be breaking nitrogen metal bonds and forming nitrogen metal bonds. So the change in enthalpies is pretty close to 0. And what that means is that the Gibbs free energy, the feasibility, therefore, of the reaction is dominated by an entropy and a temperature change. And in that case, the reaction would favor something occurring if you had essentially a positive entropy and you're increasing the disorder. And so positive entropies are generally favored, certainly the case when you've got a relatively low enthalpy change. Okay. 2492, does that answer your question perhaps in a very long-winded way? Great. Okay, so what we're going to do is we're going to look now then at a couple of examples of how we can use delta G, some simple examples here. We'll then look at the possible scenarios, the possible outcomes of changing enthalpy and entropy changes and when reactions are feasible and not feasible, and then we'll go on and look at our past exam questions. So here we go. We've got magnesium carbonate here, and we've got the reaction here where we're adding heat to this reaction and we're decomposing to form magnesium oxide and carbon dioxide. So this is a thermal decomposition. The question is, at which temperature does this reaction become feasible? So let's see if we can work this through. We've got some data. So we know this to be true, that delta G is equal to delta H minus T delta S. And what we know is that when delta G is equal to 0, we know that the reaction is going to be feasible and it's a tipping point. So in other words, we can re-express this as T delta H is minus T delta S, and therefore 0 is the point at which this becomes feasible. So we can rearrange now. So I'm going to add, I'll do this stepwise just to show you where it comes from. So we get T, that's the temperature, delta S is equal to delta H. And then I can then divide by delta S. So the temperature is equal here to delta H over delta S. And here we just have to be marginally careful because we've just got to ensure that we're in consistent units. And that is to say that we have got to ensure that we are either in kilojoules per mole for both of these values or in joules per mole. I tend to convert everything into joules per mole and then back again. That's just my preference, but it really doesn't matter as long as you do it correctly. So we have 117 times 10 to the 3 over 175. And I'm just going to put that into my calculator. So we do 117,000 divided by 175. And we get here a value of 668.57. So I'm going to round that up to 3 significant figures because that's what I'm being given in the question. And remember that this is a temperature and that this is in Kelvin. Now, for this particular example, because the enthalpy change is positive, and the entropy change is also positive, what that means is that this is the temperature and which above this reaction becomes feasible. So this is at all temperatures above 669 Kelvin. Okay, 4553. So the temperature in the equation of Gibbs free energy, the current temperature of the system. Yes, that's correct. So we could be asked in a variety of different ways there, 453, and we'll see that as we go through some more examples. Okay, so there's a magnesium carbonate, and that is temperatures above 669 Kelvin. We'll have a look at another example here, zinc carbonate, the thermal decomposition. And we've got some more data, so we've actually got to be a little bit more, we've got to do a bit more work for this question. I'll make this a bit bigger so we can all see it okay. Oh, there we go. Zinc carbonate decomposes on heating, and we got some data. Calculate delta H, calculate delta S, and calculate delta G for this reaction at 298 Kelvin. So we've got enthalpy of formation data. So if you remember, if you've got enthalpy of formation, then it's going to be products minus the reactants. So the enthalpy change here is going to be equal to minus 394 for carbon dioxide plus minus 348 for the zinc oxide, take away minus 812 for the zinc carbonate. Entropy change here. So the change in entropy is equal to the sum of the products minus the sum of the reactants. So again, we've now got 214 here for our CO2. We've got 44 for our zinc oxide, and we're going to take away 83 from that value for the zinc carbonate. So we're going to put all of these into our calculator, and we're going to check what values we get. This is when I wish I'd done some of these calculations beforehand. So minus 394 plus minus 348. And then we are take plus 812. And we get a value here of equal to 70 kilojoules per mole. Hopefully some of you have just written that down for me. Fantastic, that's good news. Just remember your per mole there. And then our entropy here, we'll put this one 214 plus 44, take away 83. And this gives us a value of 175. And just remember that this is now in joules per mole per Kelvin. Now, just as a double check, we're doing a decomposition. We've got an increase in the number of molecules and we're forming a gas. So a positive value of 175 joules per mole per Kelvin is a sensible value. Just be careful that we've got the right units. Then to work out delta G for this reaction at 298 Kelvin, well, we now use our equation that we've been using before. So delta G is equal to delta H minus T delta S. We've been given a value here at 298 Kelvin, so we're 70 kilojoules per mole. We could convert that here to 70,000. Or I'll do it the other way just to show you that it can be done either way, it doesn't matter. Minus 298 multiplied by 175 times 10 to the minus 3. So what I'm doing there is I'm converting joules to kilojoules per mole. In doing that, we then get a value. Let's check what we get. So 70, take away brackets 298 multiplied by 0.175, close the brackets, and we get a value here of positive 17.85 kilojoules per mole. Now, just be aware here that we want to ensure that we are using the right number of units. So really 3 significant figures, probably a more appropriate number here because we've only got 3 in each of the data sets at the beginning, 17.9 kilojoules per mole. The final thing to do is to decide when this reaction becomes feasible. Well, because it's not feasible at the moment, and the reason for that is delta G is greater than 0, so it's not feasible. So to work that out, we now do what we did before. And in order to work that out, we simply say that 0 is equal to delta H minus T delta S. We set delta G to 0. We rearrange. I'll do the whole thing again. T delta S is equal to delta H. And then therefore T is equal to delta H over delta S. We put in some values here. So we can have 70 over 0.175. And we're going to put that into our calculators. We get 70 divided by 0.175. It's going to increase by a fair bit. So we get a value here is 400. Remember our units here, Kelvin. So that's the temperature at which above this reaction becomes feasible. Okay. Like I say, in a couple of minutes' time, we'll go through and look at some thermodynamics questions. Check that we're happy with them. We're just going to see now the different scenarios that we've got. Okay. Thanks for the question, Kay. Why is it 0.175? Just remember here, 70 kilojoules per mole was my enthalpy change. Um, Thank you, David. You're absolutely right. And 175 divided by 1,000 gives me 0.175, which converts my entropy value into kilojoules per mole per Kelvin. Okay, great. Thanks for sharing your experiences and your correct answers there. So the final thing to be aware of here is that, well, we can plot some data and we can look at how the various different possibilities sort of span out, and then therefore what would happen with things which are feasible. So here we've got ourselves all of the possibilities for how delta G will vary depending on whether delta H is positive or negative. Remember, if we're talking about that, and if we're talking about entropy being positive or negative, we're talking about either a endothermic reaction or an exothermic reaction. And whether or not the change in entropy here is positive or negative. In other words, whether we are seeing an increase or a decrease in the disorder. And what we see, just to identify, is if we have a negative delta H and a positive delta S, delta G is always negative, and therefore we are feasible at all temperatures. If both of these examples, if we got an exothermic reaction and the entropy decreases, it becomes negative, then at lower T, the delta G is negative, and at the higher T, delta G is positive. In other words, at some value, there will be a temperature when delta G is equal to 0. Above that, the reaction is not feasible, and below that temperature, the reaction is feasible. The next example then is positive and positive. In other words, we've got an endothermic reaction in which we are seeing an increase in disorder. And in that case, at a lower T, the delta G is positive, and therefore the reaction is not feasible. And at a higher T, the Gibbs free energy becomes negative, and the reaction is feasible. So an example there would be like the thermal decompositions that we've just been looking at. The final example here is that we've got a positive enthalpy, so an endothermic reaction, in which we've got a decrease in disorder, and in that case delta G is always positive and the reaction is never feasible at any temperature. So that is obviously a useful thing to know, because it just indicates the reaction is not going to occur. The other thing that we should be aware of is, even if delta G is less than or equal to 0, we could still have a very high activation energy, which might mean that the reaction is still quite slow and takes a while to get going. Okay, so it doesn't actually give us an indication of the activation energy. And I think we'll probably come across that sort of thing when we look at the past paper questions in just a moment. All right, this year as well, because we are dealing with sort of maths in a bit more detail, they're keen to increase the amount of maths content in the exams. What they want us to be aware of, and what you should be aware of really, is that if we write the expression, and I'll do it down here, delta G is equal to delta H minus T delta S, what this gives us an expression is, we could rewrite this as y is equal to, well, it's a straight line graph, which you should be used to seeing, of y equals mx plus c. And I can rearrange this to minus T delta S plus delta H. Okay, and what we end up plotting here is an example, is that if we plot delta G against And on 4553, I've seen your question, and I'm just going to finish this little discussion on the straight line graphs, and I'll come back to your question just before we go and look at the past exams papers. Okay, so if we're to plot delta G here on the y-axis against the temperature, here we got delta G. Our x value here, we're measuring as the temperature. So what that means is we can end up with the intercept of the graph here is a value for the enthalpy of the reaction, whilst the gradient here of the graph is an indication of the entropy value. So we should be able to plot data and also identify when reactions are occurring and also what the entropy and enthalpy would be from that. Importantly, as we look at this graph, we got delta G is 0. So we can see quite clearly on this one, we're about 800 degrees Celsius. This is the point at which the reaction becomes feasible, and it's all temperatures below 800 Kelvin. And if we were to go back to our example here, we're looking at a reaction where the reaction is feasible at low temperatures. So that is this example here. We got a negative delta S. Well, that makes sense because we've got a positive gradient, but our gradient here is negative delta S because we're plotting temperature on its own. And we've also got here, we can see a negative enthalpy change because we cross the y-axis at the negative. Okay. I'm just going to have a look here at the question from 4553, and then we'll spend 25 minutes or so having a look at some past exam questions. Okay, how does delta G determine if a reaction is feasible? How does enthalpy change, entropy, and disorder relate to each other? Okay, good question. Well, I think the I'm just going to take this question from 4553, and then I'll come back to Jay about the negative gradient bit. How does delta G determine if a reaction is feasible? Well, it's not so much whether delta G determines if a reaction is feasible. It's sort of more the other way round, is that we've always looked at reactions in terms of enthalpy changes. And in fact, what we've never included here is a discussion as to why some reactions occur. So if we were to look at an example, let's say where we've got a metal complex, is probably the one that we've seen more often. Just as a point of note, I have seen the question about the negative gradient, and I'll come back to it. If we look at the reaction, the chilate effect, where, and I'll just do a square planar complex here. Now, the reaction has to go for a reason here. All right, if I add let's imagine we added some sort of porphyrin ring, which actually replaces all of the reactants here. Now, this reaction, now I'm just going to draw the porphyrin ring as sort of some links, all right? So apologies for not knowing what a porphyrin ring looks like offhand. Okay, so the porphyrin ring is importantly one multidentate ligand, and we get +4 ammonias. Okay, and we got here nitrogen porphyrin ring. There we go, with our mold, and we've just got one of those. That's our reaction. Now, essentially, there is no change in enthalpy. All right. So the question here, oh, I hate it when it does that. There's no conceivable explanation here as to why the reaction actually goes. It has to go for some sort of thermodynamical reason, but what we know is it is not down simply to an enthalpy change, because this is about zero. So there has to be a second driving force, and the second driving force is this extra entropy value. The idea that, and this is the second law of thermodynamics, that the universe is moving towards a state of positive entropy. Things are trying to get more disordered. It's why essentially the universe is expanding. Everything's trying to get further away from each other. into a more disordered state. So that is a driving force, and the combination of energy changes in a reaction along with the entropy change is why reactions occur. And it so happens that we observe this for the unique cases when delta G is less than 0, when we have this combination of enthalpy and entropy. All right, now we don't need to answer that in the exam, but that's where that comes from. 4553, I hope that deals with your question. Now let's hear other words. I'm then just going to move on to Jay's question about the gradient. Now, Jay's question, I completely understand. This looks like a positive gradient. Now, if I was to look here at the equation, just recall here that my m here is the gradient, x is what I plot on the x-axis, y is what I plot on the y-axis, and c is the intercept. Now, if I separate out this equation so it's a little bit more obvious, I'm plotting positive t. So actually, my x value here, if I'm going to draw it out, is the same as the straight line equation, is actually t here. M is minus delta S. Okay, that is what my gradient is, and my intercept, my y-intercept, is delta H. So what that means is the gradient from this graph is made up from simply the negative of the entropy value. Because this is a positive entropy, my change in entropy must be a negative. Jay, does that answer your question? Yeah, no, I completely understand that it's difficult to imagine. All right, let's have a look. I'll try and get, so my plot here, and what we're going to do is I'll replot it. Excuse my bad drawing. Okay, so I've got delta G is what I'm plotting on the y-axis, and I'm going to plot this against temperature. My equation, remember, for a straight line is y equals mx plus c. All right, and we're using the equation delta G is equal to delta H minus T delta S. The plot that I had before, all right, looked a little bit like this, where I had, you're absolutely right, a positive gradient. Now then, if I'm going to look at each of these values, the y values, we're quite happy to identify those as delta G. So y is delta G. X in this particular equation is, I'm plotting as T. All right, notice that it's positive T. It's not a negative T. So that deals with delta G and the delta T. No worries. What that leaves me with then is the gradient and the intercept. The intercept I'll do here in green. So the intercept, that is where I cross the y-axis, is my enthalpy change. So here I have delta H. And what that leaves me with is the final step here, which is a measure of the gradient. Now the gradient is a change in y by the change in x. The gradient, m, is, like you say, clearly a positive value here. But in my equation, if I extract what I've got left, I've only got minus delta S. So my gradient M is equal to minus delta S. Therefore, in this example, a positive gradient is equivalent to a negative delta S, whilst a negative gradient would be equal to a negative delta S, which would be equal to a positive delta S. So does that help with our understanding of where that graph came from, and also how I got a negative value for the delta S on a positive gradient? Brilliant. Smashing. I'm really pleased that's helped clear that up. David, hopefully you also with us on there. Okay, I'm just going to take a pause just for a second. I'm going to leave that up there, and I'm then just going to jump across. If you've not already done so, we're going to have a look here at question 13 on the exam question. So I'll just jump across. Question 13. Let's see if I can find it. There's heaps of questions here to keep you going. 25. Here we are. So we're on page 26. Like I said, there's heaps of questions. Just going to have a quick drink here, and then we'll have a look at these questions. Okay, so hopefully you've got a hold of the questions here, and you can see them. You've either printed them out or you can see them on the screen perhaps. The answers to all of these questions, if you're wanting to get a hold of them at all, are in the thermodynamics section of the past webinars, and you can pick them up here if you need them at the end of the session. There's also the past paper questions here as well. And again, as with all of our webinars, there's also a copy of the webinar screen. Let's have a look then and see how we can go with some of these questions. Here we go then. So here we got a picture of entropy. Note that we start at 0, 0 here. Suggest why the entropy of water, so this is of water here, is 0 at 0 Kelvin, and the reason for that is that they are in a state of complete order. Okay, so the simple thing is to say the most order or maximum order, because that's what we're always looking to answer with in terms of entropy questions. We're describing a comparison in order. What change of state occurs at temperature T1? Well, hopefully that would be okay. You're seeing two changes of state. That's key. The sharp lines indicate a change of state, and you're only seeing two. So you're going from the solid there to the liquid. So you would go for, make sure you're going for melting. Explain why the entropy change delta S at temperature T2 is much larger than the entropy change at T1. All right. And so the key that you want to say is that there is this is a slightly odd question, to be honest with you, but what they're looking for is that there is an increase or a bigger increase in disorder, and you might qualify this at T2, i.e. when a gas is formed. If you're wanting to know what, if you think about disorder, I sometimes think about if anyone plays snooker or pool out there. If you think about a triangle of snooker balls, if they've got in a triangle, they are at the most ordered. If they're moving around, and let's say you take some of them out and they can still move around, they're jumbling around perhaps like a liquid, then there is a slight increase in disorder, a bit like we're going from solid to a liquid. But if you take that triangle off and then you hit it with the white ball, your snooker balls end up all over the pool table and they are completely disordered and no longer showing any sign of order whatsoever, a bit like a gas. Okay, then we're on to the question here. It requires 3.49 kilojoules of heat energy to convert 1.5 grams of liquid water into steam at 373 Kelvin and 100 pascals. Use this data to calculate the enthalpy change, delta H, when 1 mole of a liquid water forms 1 mole of steam at 373 Kelvin and 100 kilopascals. And I've just realized a question that we actually need to sort of jump onto in just a minute. So the first thing to do here is to work out the moles of water. So the moles of water here are 1.53 over 18, because that's the amount of water, of course. So the moles of H2O, and that's equal to 0.085, and the heat change per mole, which we're given here as in kilojoules, is going to be 3.49 kilojoules divided by the number of moles, which is 0.085, giving us a value here of 41.1 kilojoules per mole for this question. What we're then going to go and do is write an expression for Gibbs free energy. So we've seen this lots of times. Delta G is delta H minus T delta S. So simple marks for doing this. And then for the conversion of liquid water into steam at 373 Kelvin, so that's 100 degrees Celsius and 100 kilopascals, delta G equals 0. Calculate the value of delta S for the conversion of 1 mole of water into steam under these conditions and state the units. So we've seen this several times. We've got delta G is equal to delta H minus T delta S. There's no marks for that because we've already got that for the previous question. We don't get any marks for stating this bit, but I'm really just doing it for completeness. 0 is when we get feasibility, and then we can rewrite this now as T delta S is equal to delta H, and then we rewrite let me check what we're looking for. Calculate the value of delta S. Okay, so in this case, I'm getting carried away. Delta S to H over T. So as we now put that through, now we use a value from the previous question, which was 41.1, or if we weren't sure, we're welcome to use the value here. I'm going to use the one from previously, which is 41.1. over the temperature. Now remember to ensure that you're using Kelvin here. So that's 41 divided by 373, and that gives us a value here of 0.110, and here we got kilojoules per mole per Kelvin because that's what we've calculated. Now strictly speaking, we'd often convert that back into joules per mole per Kelvin, and that'd be 110 joules per mole per Kelvin. But they didn't mind here whether you gave kilojoules per mole per Kelvin or joules per mole per Kelvin, as long as you had the figure correct in the first instance. Now, What I've realized is that there's a nice specimen question here, which I've forgotten about. We looked at the specimen paper here from the paper 3. Some of you have been asking if I'm going to make these available. The answer to that is yes. I will make them available at the end of next week. There's 3 specimen papers on the AQA website, which I will put up on the site. This is a question about Le Chatelier's principle at the beginning. We will be looking at KP and KC next week, which is sort of starting off the question. But as we move on, we then move on to a question down here. I'm just going to repeat the equation because it's CH4 plus H2O to make carbon monoxide plus 3 hydrogens. So H2O to make carbon monoxide plus 3H2. The first question here says table 3 shows the standard enthalpy of formation and the standard entropy for each substance in the equilibrium reaction. So they give us enthalpy of formation data. So this is actually synoptic because working out the enthalpy change of a reaction using formation data is an AS question. And if we've got formation data, it's products minus reactants. Remember, if we had combustion data here, it would be reactants minus products. But because we got formation, it's products minus reactants. So the enthalpy change, delta H, for this question is going to be, well, 3 lots of 0. I can probably do that one off my head without too much worry. So we've got 0, 3 times 0. I'll put it all in just so we've got it there. Plus our carbon monoxide, which is minus 111. And we're going to take away from that the value of water plus the value of the methane minus 75. Put that into my calculator. Minus 111 minus 242 and added to minus 75. Close up all my brackets. And I get a value here of the enthalpy change to be equal to plus 206. How do I know which are the products? Okay, so it's a fair point because we're talking about an equilibrium reaction. We're talking about the formation of hydrogen. So we assume that if we're talking about a formation of hydrogen, then the products must be on the right-hand side. Yeah, there was an equation, David. It was sort of at the top, which is why I repeated it further down. Sorry about that. Hopefully you could see it. Then the entropy, so the equation we got given was this one. Sorry, I jumped. No worries at all. The entropy, so the entropy change here is the products minus reactants. So in this one, we do have to include the hydrogen this time, which is this time 3 times 131 plus 198. And we take away from that 189 and 186. We pop those into our calculators. 3 times 131 plus 198. And we take away 189 plus 186. And we get a value of 286. Now that makes sense. We're all in the gaseous species, but we're 216, not 286. We are all in the gaseous state, but we've got an increase in the number of molecules. Now, I've just read, of course, the question properly. Standard enthalpy change is 206. I've just been walking through to try and get to the answer for 7.4. Then says use your answer from 7.3 and the entropy data from table 3 to calculate the minimum temperature in degrees Celsius. We could use a value here if we needed it, but we've just worked it out up here. So again, we're now on delta G is equal to delta H minus T delta S. We simply need to rearrange, say 0 is equal to delta H minus T delta S. It's probably worth pointing out that the reaction becomes feasible when delta G is less than or equal to 0. We rearrange to the temperature times by the entropy, and then we can rearrange for the temperature. You don't have to show all of these steps. The key things to point out for your marking really if you're is your equation, and I would always point out that reactions are feasible when delta G is less than or equal to 0. Finally, we just need to put some data in, making sure that we include sensible values. So we're now 206,000 over 216, or you might have done 206 divided by 0.216. It doesn't matter how you do that. Just remember, all I'm doing there is I'm ensuring that I'm using the same units. I put my data in, and there we get the minimum temperature, remembering to use 3 significant figures because I'm using that's data which has got 3 significant figures. I get 954 Kelvin, and I just notice here that they're looking for it in degrees Celsius, so I've got to take away 273 from this value. And I get 681 degrees Celsius. Okay, so they add in an extra step there to point out that you need to know that you're working in Kelvin. Okay, we'll jump back now. Like I say, that was from one of the specimen papers that was live. We'll jump back to our past exam questions. We'll try one more of these, and then I think we'll call it a night, because I think otherwise my cough's going to take over. Okay. Let's see what we've got on the next page. I can hear a couple of questions coming through. Oh, good. What did I think about the specimen papers? Well, I'll tell you what I think about them compared to the biology and the physics. I think the chemistry papers are a lot more realistic. There's quite a lot of them in there, and I also think the paper 3s are particularly difficult because of the multiple choice questions. Like I say, we'll look through all the specimen papers in the coming weeks. I'll make sure they're available and to highlight good ways of attacking them, really, to give you as much assistance as possible. All right, this question looks very similar again, so I'm not going to go through a question quite so similar as the one we've just seen before. Why this line obeys? Let's have a look, see what the rest of this question. Oh, there's an interesting one. So figure 2, I'm not going to go through this now, but question 2 here shows the free energy change for a particular gas phase reaction varies with temperature. Why the mathematical equation for a straight line y equals mx plus c. So really what we're looking for there is for, it's in the key points, is for an explanation there of y equals mx plus c for a straight line and pointing out each of those key points. I'm not going to go through that again, but just to show you the sort of things you might expect us to do. I'll find one more before we call it a night. Let's see what 32 is, page 32. Here we go then. So again, we're seeing much similar questions, lots of times calculating delta S. Here we've got formation data, so remembering enthalpy of formation data. The enthalpy of a reaction is the sum of formation data of the products minus the reactants. And that's the reverse of the question we've just seen. All right, so there we go. That took them an awful lot of time to work that out. So I'm not going to go through this question either because it's exactly the same as the specimen paper that we just done, apart from it's methane plus water going to carbon monoxide plus hydrogen. This question is carbon monoxide plus hydrogen going to make methanol and water. Oh, wait, we could do this one. Let's do this one. So we've got slightly different because we're now making methanol from carbon monoxide and hydrogen. So it's carbon dioxide, apologies. Let's go through the steps for this one. So enthalpy change, delta H here is equal to products minus reactants. So enthalpy change is going to be products right-hand side, so methanol minus 201 minus the water, which is plus minus 242. We'll bracket that. Take away brackets 3 times 0, which is always 0, plus minus 394. We're going to rattle that into our calculator nice and quickly, and hopefully we're going to get a value round about minus 49 kilojoules per mole as we put that in. Then we're asked to calculate the standard entropy for this reaction. Again, we're products minus reactants. This time hydrogen has a value, notice, so we do need to include that in this reactant. So we're now 238. So we're products minus reactants again for the entropy. So we're 238 plus 189. And we're going to take away there 3 times 181 plus 214. As we pop that into our calculators, hopefully we're going to get minus 180. Just remember your units to ensure you get them correct with joules per Kelvin per mole. Then we move on here. And we're asked to calculate the temperature at which the reaction becomes feasible. So key mark, delta G is equal to delta H minus T delta S. We're going to pick up a mark for that. The reaction becomes feasible when delta G is less than or equal to 0. So make sure you include those two statements. Feasible. Okay, and then we've got to use some data. So we're going to have 0 is equal to delta H minus T delta S. Again, I'm just going to write it out this time rather than putting all the data in. I'm going to pick out those two values from the previous one, which is minus 49. I'm going to convert it to joules, so 49,000 over minus 180. As I put those both into my calculator, we should remember get our value in 49,000 in degrees Kelvin. I put that in and I get a value here of 272 Kelvin. So the final thing is suggest why the industrial process is carried out at a higher temperature than the one you have calculated. And that's simply going to be we're at a higher temperature, and that's because the reaction would be too slow at low temperature. The reason for that, if you look at what we're dealing with, we're looking at water, and water would actually be ice at that temperature, and therefore you're very unlikely to get any reaction occurring when water is ice. Finally, we've got 2 more questions here. Write an equation for the complete combustion of methanol. Use your equation to explain the combustion reaction. The gas phase is feasible at all temperatures. Okay, so you've got to think here. So methanol plus oxygen. We're going to make CO2 plus water. Let's balance that up. 1 of these, 2 of these. We need 3/2 oxygens. So the thing about this is we know that the enthalpy change of a combustion reaction is negative. And we are also seeing a positive entropy change. So I go back to my discussion earlier on. If I have a negative enthalpy and a positive entropy, the key thing is to point out that delta G is always less than or equal to 0, because enthalpy is negative. So in that reaction, delta G is equal to delta H. So this is always negative. And you're always going to be taking away a negative value because the entropy is negative. And so delta G is always negative and therefore always feasible. Give one reason why methanol synthesized from carbon dioxide and hydrogen may not be a carbon neutral fuel. If you're reasons why you might not got things which are carbon neutral is there's always going to be some sort of transport association, which means that you're going to get CO2 formed. So transport of chemicals uses CO2 or releases CO2 is probably a better term. Okay. There's lots more questions here going through very similar sorts of questions as those on Gibbs free energy and entropy change. Hopefully that's helped. Like I say, next week we will be looking at KP and KC, and also we'll be looking at period 3 oxides, which will pretty much bring most of the revision webinars not to an end, but that will cover most of the topics. Although if you've got any questions, if you've got any topics that you really want to work on, do please give me a shout. These happen to be the 2 questions I've had the most of most recently. And Wednesday's webinar, we're doing practicals, and I will go through percentage uncertainty because I keep getting questions about multiplying error values by 2. And I think it would be helpful. Sorry, said, can I answer the first bit? Did I? Sorry, did I miss a question? Use your answer to explain why. I missed a question. Did I? I don't think I did. I think I got it. Part of the long question. Use your answer part A and B to calculate why this reaction is not feasible at high temperatures. Oh, okay. So why it's not feasible at high? You're right. I did miss that question out here. So the reason it's not feasible at high temperatures here is because of the no, you're right. I didn't explain that. You're absolutely right. Apologies for that. So the reason that it's not feasible at high temperatures here is because of the entropy changes. So at here we had a negative enthalpy and a negative entropy, I think. And what that means is at higher temperatures, delta G is positive. So you're right, I didn't answer that, but that is our reason for that particular example. Okay. So, like I say, next week, the evening webinars, we'll look at KP and KC, period 3 oxides. The practicals, we will look at 2 more required practicals, and we will also look at percentage uncertainty. I hope you found that useful. Don't forget to share the website with any of your colleagues at school, or do please feel free to share it on any social media as well. It would be great to have as many of you as possible. Keep any questions coming. If you've got any particular topics that you're struggling on or that you'd like me to spend a bit of time on in the webinar, please do just ask. Otherwise, I'll say good night for this evening. Have a really good weekend. I hope the weather's good to you. Get plenty of work done. And don't worry, the long summer will be with you before you know it. All right, take care and good night.